Hello, welcome to the course Electronic System Design. In the last lecture we discussed about the simulations, how do we perform this on the SPICE software, and we first saw there is a operating point analysis which is the steady state analysis where we have a circuit and we want to find the initial condition at time t equal to 0, how the circuit is biased. We want to calculate all the node voltages and branch currents so that we know all the parameters at the steady state value when no signal is changing. However, when we want to perform certain type of analysis, we need to do DC simulations where we want to sweep a parameter and want to check how the circuit is performing at different parameters. There we took example of a temperature. For example, temperature is a very general parameter which affects almost all electronic circuits. So, we are given a circuit, a active circuit or a passive circuit, and we want to sweep the temperature from a very low value, let us say minus 40 degree, to a very high value which is 125 degree, and during this temperature change we want to analyze the circuit, how the circuit is performing, the output is changing. So, that we can do by DC simulations where we are sweeping the voltage or sweeping any parameter without any knowledge of the time. So, there is no change of time for a circuit, only the change of a parameter. So, temperature is only changing, there is no information of time in the DC simulations. The next type of simulations are transient simulations, which we are going to discuss today. In transient simulations, there is a operating point analysis first which SPICE performs. Why do we do operating point? Because we want to know the initial conditions of the circuit. For example, if a capacitor is charged to some value, there is a charge storage or the inductor is flowing some amount of current. So, those are the initial conditions of circuit at time t equal to 0. And then we are applying a signal which is starting right from t equal to 0 to a next instance which is 0 plus delta t. So, these are transient simulations where we have now the knowledge of time as well, how the output is changing with respect to time. Okay, so, to start a transient simulation, it is important to note that SPICE is going to do a operating point analysis first, so that the SPICE knows all the node voltage and branch currents, then only the transient simulations will start. So, even if we do not specifically write that we want to do OP analysis first before the transient analysis, SPICE is doing that internally, finding it a steady state value of the circuit and then changing the signal with respect to time and find out the individual voltages, currents or whatever is the output with respect to time. So, these are called transient simulations. The earlier one was DC simulation. So, this is we are going to discuss today. Before jumping into the transient simulations, first we want to study something called data sheet of components. So, last lectures also we discussed that we have so many components available in the market and not all the models are available in LT SPICE, which we are using for this simulations. So, those components, if we want to use them in our circuit, we want to know first what that component actually is. So, for example, a diode, if we want to pick a diode from the market, there are so many diodes available in the market, even thousands of diodes within a certain range and within certain reverse bias and so many parameters. For the same set of parameters, there are hundreds of diodes available in the market. So, which one will be good for our application, that we should know, and that we can know by the data sheet of that component. So, today first we will discuss how the data sheet of a component look like, how do we read the data sheet, and then we will perform the transient simulations. So, let us discuss the data sheet of sample diode. So, for example, I take a very general purpose diode which is 1N4007. So, we take this diode which is very general, very commonly used diode 1N4007. So, this is a diode which we are going to discuss. How to get the data sheet of this diode? This is typically downloaded from the manufacturer's website. Whoever is manufacturing this diode, they also provide this data sheet on their website, so that we can download. And that, for example, for this diode you can find over this link. So, this is a link for this particular diode. Similarly, you can find other components on you can use any search engine such as Google. You type the component name and you can find the website URL of manufacturer. You can download the data sheet. When you open this data sheet, this is how this data sheet look like. This is a big PDF document, typically more than 10 or 20 pages. So, first we need to find out which model we want to consider. For example, we are considering this diode 1N4007. So, this data sheet is actually common for many diodes. For example, this is 1N4001 and we are interested in this diode 1N407. The peak repetitive reverse voltage or the DC block voltage is 1000 volts. So, this is the voltage which this diode can bear across it, and non-repetitive peak reverse voltage is 1200. So, there are certain difference in these voltages. This is non-repetitive. Once in a while 1200 volt also can be safely applied across this diode. Reverse voltage is typically 700 volt. Average rectified forward current is 1 amp. So, these are all the parameters which we need to find out while we using this diode in our circuit. If our circuit demands 1 amp type of current, we can use this. Otherwise, if our circuit demands more than 1 amp, then we cannot use this particular diode. We need to find out some other diodes from other manufacturer for that analysis. So, this is how a data sheet look like for a diode. These are some electrical parameters. Alongside the electrical parameters, there are some more important parameters which we call the thermal parameters or the thermal characteristics here. Here if you see, we have some electrical components and we want to use these components in our circuit. When this diode, particularly this diode, is burning 1 amps of current inside this diode, then there is a certain amount of heat dissipation inside the component. So, we have a diode and this is working in the circuit, and because of the current flow in the diode, this diode is going to slowly heat up because of power dissipation. So, how much heat this diode can handle? These are specified by these thermal parameters, and this is what we know by the junction temperature. So, how much maximum temperature or the junction temperature it can withstand to reliably work in a circuit. This is what given by the thermal parameter. So, the symbol of this parameter is this R theta J A, and this specifies the maximum thermal resistance or the junction to ambient maximum thermal resistance what it has, and the maximum rating of this is given in note 1. So, this we are going to see next. How this thermal resistance is linked with the junction temperature is given by this equation, which is very general equation. So, Ta is the ambient temperature, ambient we generally calculate by the room temperature, which is 27 degrees. Pd is the power dissipation, how much is the maximum power which is dissipating in the component, and R theta Ja is the this thermal resistance, which is given by this. So, junction generally ambient temperature is constant, which is let us say 27 degree. Pd is the maximum power dissipation which the component is allowed, and R is the maximum thermal resistance. So, we know all these values, so we can calculate how much is the maximum junction temperature, and junction temperature is typically we have certain limits at the system level. For example, the junction temperature should not be more than 100 degrees. So, if we know Tj value, then we can come up with the maximum power dissipation we can allow in the component. So, any power more than that maximum power is going to burn that component. So, here we have this formula by which we can calculate how much power is going to be dissipated in the component when we are using this in our circuit. If our circuit demands more current or the more power dissipation, we need to have, for example, the heavy loads, for example, the ACs or the heaters or something, which requires a high amount of current flowing in these small PCBs. That time we need to figure out the components which can handle that much of power, or that their maximum thermal resistance is lower, so that they can dissipate that amount of heat to the environment. So, this is the equation to govern how much is the junction temperature is going to be. So, here we see this maximum thermal resistance is not given a unique value here under this maximum, it is given note 1. Note 1 is a separate table which says here that this this thermal resistance is dependent on how you mount this component, because for example, we have a component, this is heating up because of power dissipation. Now, how much heat will be dissipated from this component to outside to the surrounding, it depends on what is there in the proximity of that component. For example, this component is put in a very close vicinity of other components. So, there is not much of a power dissipation from this component to outside environment, because this heat will be blocked by other components. So, depending upon how we place this component on a PCB, it dictates how much the thermal resistance is going to be, and the lower the thermal resistance is the better for the power dissipation. So, here in this table, in this data sheet itself, if we see, we have this typical values of R theta J A, and this is dependent on mounting methods. So, here it is given method 1, where we are putting this diode very close to the PCB. This is our PCB, and this diode is dissipating this heat, which is going to be dissipated to outside environment, but here this side the heat dissipation will be very less compared to the top. So, the junction temp or the thermal resistance is going to be higher in this case. However, in this method 2, if you see, this is PCB and we have kept a certain amount of gap between this diode and the PCB. So, the heat can easily dissipate from the top as well as from the bottom. So, the thermal resistance is going to be less in this case. There is one more option where we can mount it like this. So, this lid is like this is, by the way, through hole component. So, one hole is put here and the other lid is coming all the way in this U shape. Now, this can dissipate in all the direction. This is also a method to mount this. However, if we see this lead length, here it is smaller, here it is bigger. However, in this case, these both lead lengths are same, which is L this side and L this side. Sometimes this is also critical while we are designing high performance PCBs. So, this is how you read a diode data sheet or any component data sheet, for example, transistor or BJTs or any other component you buy from market, you download from the website and go through all the parameters given in those data sheet. Electrical parameters are important for compatibility, how do we connect that on circuits. However, the thermal characteristics or thermal parameters are equally important because they are going to define the reliability of your circuit or your PCB, whatever you want to design. So, this is about a little bit about the data sheets. Now, next let us discuss about the transient simulations. How do we perform these kind of transient simulations in the LT Spice? So, we go to the LT Spice software. So, we open LT Spice, which look like this. We go to new schematic and then we make a very simple circuit. We take a ground connection first, then we take a capacitor, take one resistor, and one source, which can be now the time varying source, and let us connect them together. So, this voltage source now, if you right click here, it is asking for the DC value. However, we are interested in the time varying signal. So, we go to advanced and we choose, let us say, a sine wave signal and put the values over here. So, the DC offset is, let us say, 0 volt, amplitude is, let us say, 1 and frequency is, let us say, 10. We just put few parameters for this source. Resistance value we randomly put, let us say, 90 kilo ohm, and our capacitor is, let us say, 18 nanofarad. So, this is our complete circuit where we have this resistor and capacitor connected together, and the signal is applied through a sinusoidal source. Let us name the mesh as well, the label net, we label it, let us say, V1, and put, let's say this is 10 kilowatt, this is the output. Yeah. So now we need to perform the transient simulation. So we go to this configure analysis and choose the transient simulation. It just need the stop time where we want to stop the simulation. So let's say we go to 200 millisecond and we put it here. So now the circuit is complete. We have a sinusoidal voltage source, which is the magnitude is between 0 and 1 and the frequency is 10 hertz, and we want to simulate this circuit for 200 milliseconds. So let's simulate it, and you see this is the simulation. Let's say see this at trace. If you see on the x axis, it's already 0 millisecond to 200 millisecond, which is time on the x axis. Now we add the traces. First is we want to see the input voltage which we are applying, so which is V1. So the voltage at V1 we want to see. This is sinusoidal voltage source, and we also want to see the output voltage, which is right here. So you see this input is the green one, which is at 10, which is given here, and if you see the output, which is blue color, there is a difference in the time, which is because of the capacitor, because the capacitor is lagging the signal. So that's why the output is little bit lagging from the input signal V1, which is green. So and there is a delay in the circuit in between the output and the input. So here you see this value is very small, not very significant. There is a small amount of delay here. However, if we simulate again for very high frequencies, for example, we go back and change the sinusoid voltage source, instead of 10 we make 100. Frequency is 100 now, and we do the same simulation. Now we see the output versus input. This is our input, and if we want to plot the output and you zoom in, just click and drag it. Now you see there is a large amount of delay in the output compared to the input. This is because now the frequency of sine wave is very high. So for that particular frequency, the impedance of the capacitor is different compared to the low frequency. That's why we have a different time delay, or we can say the phase delay in the circuit, because the frequency is different. Here you see this is very high, and if we do the same simulation at a very high frequency, for example 1 kilohertz, we increase it 10 times, You see, this is the phase delay, which is very high from here to here, from this peak to this peak. This is the phase delay, which is very high. Also, although the output magnitude is also reducing. In the first one, we saw there is a comparable output, comparable to the input. However, now the output magnitude has also decreased. So, the magnitude and phase of the output depends on the operating frequency of the signal. This is we can measure in the transient simulation. So, this is how we perform transient simulations, where we make the circuit and put a spice directive which is .tran and the time at which we want to stop the simulation. This is the complete simulation for 200 millisecond, because the frequency is high. So, now we have so many cycles which we have calculated. So, this is how we perform the transient simulation. However, to analyze different type of things, we do much complicated transient simulations compared to this. Now, let us discuss one more type of simulations, which are frequency domain simulation. So, we discussed transient simulations where we sweep the time and we want to check the output of a circuit with respect to time, how this is going to change. When signal is coming, let us say 5 volt, what is the output? When 5 has become 6, what is the output? So, this is some sort of transient simulation. However, we use components, for example, capacitors and inductors. These components, the impedance of these components is actually frequency dependent. This is what we saw in this example. When we are changing the frequency, the output is changing with respect to time. So, one is the time axis where the output is changing, also the magnitude and phase, that is dependent on the frequency, how much frequency we apply. So, now we come to the point that we are using all these components in our circuit, inductors and capacitors. How to solve them, how to intuitively think about these components, where the impedance of these components, the working of this component is dependent on the frequency, not on time, but the frequency of the signal, which the signal we are applying on these components. So, to analyze these kind of components and these type of circuits where we use inductors and capacitors, it is easy to visualize them or to guess or to interpret the output in frequency domain. Now we are talking about the domains. So, the first one is the time domain or the transient simulations. This is what we perform just right now. This is the transient simulation, or we call it time domain simulation, where we are looking at the outputs with respect to the time. The time is changing and we are looking at the output. In a different domain, we do not want to see the output with respect to time, we want to see the output with respect to frequency. So, that is called the frequency domain simulations, and that these are very important to visualize the circuit or to know the circuit behavior accurately, which is not easily understood in time domain. So, let us see what is frequency domain simulations. So far, we have worked only on time domain analysis. and DC analysis. Now let's enter the frequency domain. So we call this frequency domain by various names. One is the frequency domain analysis, so this frequency domain refers to the analysis of mathematical functions or signals with respect to frequency. We sometimes also call it the small signal analysis. This is actually the linearization of circuit characteristics. At certain DC bias point. With small magnitude of variables. And the other point is the AC analysis. AC means alternative. Current. signals in frequency domain. So now we have a frequency domain where the x-axis is frequency, not the time. And if we think about the x-axis now, we have 0, which is 0 frequency. It means the signal is DC, and when we are increasing or going away from the origin, the frequency is increasing and from 0 to a very high value. So x-axis is our frequency, which is the operating frequency of the signal. And now we want to plot all the variables in this as a y-axis. So y-axis is the parameter and x-axis is the frequency, not the time. So that is called frequency domain analysis. And what we do in this, we perform a small signal analysis. What is the meaning of small signal here? That we have a circuit and all the circuits have certain degree of non-linearity. The output is not linear with the applied parameter. But in our simulations, to solve the circuit, we assume that everything is linear at a particular DC point. So what is the DC point is? As we said, any simulation, when we perform, let us say transient simulation, DC simulation or anything, first SPICE goes back and perform the operating point simulation, where it calculate all the node voltages and branch current. That is the operating point of that circuit. So that point where the circuit is stable in time, at that particular DC point, whatever is the non-linearity in the circuit, that non-linearity is assumed to be linear at that DC point. So that is the meaning of small signal analysis, and in this we use the concept of linearization of circuit characteristics. So this is happening at a particular DC point. The third is the AC analysis, where we change the signal by a applied frequency and we plot in the frequency domain. So generally we call AC small signal analysis or the frequency domain analysis. So why this is so important, this type of analysis, why these are very important for understanding the circuit? Because all the components, not even capacitor and inductor, but even all the components, whenever we manufacture it, there is a surrounding which is available to those actual components. Actual, for example, diode, this is of semiconductor material, but this semiconductor material is put in a casing which is ceramic, and this ceramic, which is extra just for the protection of the device, this offers certain amount of capacitance from this diode to the external world. So this capacitance is called parasitic capacitance, which is unwanted. We do not want this capacitor to be there, but to make it a real diode, we need to put something, and anything we put that offers some parasitic capacitance. So whenever there is a capacitor, we need to deal with the frequency characteristic of this capacitor. On the other hand, this diode also has two lead wires coming out from both the ends to mount it on the PCB. This is also important. This is also we need to connect it in a circuit, and whenever we have extra lead wires, these wires offer certain amount of inductor. So even if we do not want it, these inductors are always there, and we call it the parasitic inductors, which we cannot ignore at high frequencies. So now think about any components, anything, BJT, MOSFET, resistor, capacitor, everything. All these components has certain amount of capacitor and certain amount of inductors in them, which are built in. And if we want to analyze this circuit, we have to understand the behavior of these capacitor and inductors, and to analyze that we need frequency domain simulations. These are not easily understood in time domain simulation. That is why these frequency domain simulations are very important. So, let us note it down that all these capacitors and inductors, even all the components, has certain amount of capacitors and inductors which are parasitic. All real components has parasitic capacitors and inductors. So, let us understand a typical component and take into consideration these parasitic capacitors and inductors. So, let us take a real capacitor circuit model. So, let us have a capacitor which is denoted by this symbol. This is a capacitor we want in our circuit, which is given by C. This is the capacitance of this capacitor. Now, this capacitor, whatever it is made up of, let us say semiconductor or any other material, whenever we have a casing around it for its protection, we always have, because these materials are not perfect, so first of all we have some impurity in the material, and which causes certain amount of leakage in the capacitor. So, that we can denote by this R leak, which is a resistance leakage. So, this is the resistance which is causing certain amount of current which can leak through this capacitor. Ideally, there should not be any current, but in real components there is always some leakage current. Next, we put casing and we put lead wires. So, they are going to introduce some series resistance, which is, let us say, extra series resistance or ESR, and certain amount of inductance which is coming from these lead wires. Let us say we call it ESL. So, this is actually the accurate model of a real capacitor. Ideally, we need only this capacitor, but in reality, along with the capacitor, we find all these components together. So, let us analyze this, what the impedance of this capacitor is. So, Z is nothing but ZC in parallel with ZR leakage plus impedance of ESL plus impedance of ESR. We can just do some approximation and it comes out. Let us say we ignore this for time being. So, let's this thing come out as 1 over SC plus impedance of inductor is SL plus ESR, which is the series resistance of lead wires. Now, if we plot the impedance of this component, with the frequency on the x-axis. This is the frequency axis, and this is the impedance, which is Z, which we are plotting here in ohms. So if we plot this component 1 over SC in frequency domain, this comes out to be like this. With increasing the frequency, this value is going to drop linearly here. This component is 1 over SC, or the impedance of a capacitor. Now if we plot the value of inductor, this comes out to be something like this. This is SL, and now here we can see that actual impedance is nothing but the sum of all these values, and let's say our ESR is at this point. Our ESR. So our actual impedance is nothing but the algebraic sum of all these three parameters. So if we plot the actual impedance at low frequency, this 1 over SC is going to dominate. So at lower frequency, the output or the impedance will be this red line, and at the higher frequency this SL is going to dominate. So this is going to be our impedance at high frequencies, and at this particular frequency, which we call the corner frequency or the resonant frequency. At this particular point, this 1 over SC is going to cancel out the SL, and at this point the actual impedance is going to be only ESR. This is going to cancel out this parameter. These both going to be cancelled out, and the actual impedance will be ESR. So at this point, sharply the impedance will go to the ESR value, and this is the actual impedance of our capacitor look like. So here we see this is the corner frequency at which this change is going to be there, where 1 over SC is going to resonate out the SL, and the actual resistance will be only ESR. So this is happening at omega equal to omega naught, which is the corner frequency, and this corner frequency is given by, we can do some math and calculate, this is going to be 1 over under root LC. So this is how an actual capacitor is going to look like when we plot the impedance with respect to frequency. So when we have these impedances which are changing with respect to frequency, and we want to analyze the circuit in frequency domain, let's see what and how it look like in frequency domain, the same signal which is there in the time domain simulation. So that analysis we do by a transform, something called FFT or the Fourier fast Fourier transform. By that analysis, we can calculate the time domain signal into a frequency domain signal. So, in fast Fourier transform, it computes the discrete Fourier transform of a sequence. So, that we can see from this graph. If you see, this axis is time axis, where this signal is changing with time, and this is going here up, going down, and this is kind of a signal which we are applying on a circuit. This signal is nothing but the algebraic sum of multiple frequencies. So, if we take few sinusoidal frequencies and add them together, they look like this kind of signal, and any signal can be represented by sum of sinusoidal waves. That is a theorem. So, this time domain signal is very hard to see how this signal is changing and what it means, but if we closely see, this signal is nothing but the addition of these three frequencies. This is, let us say, frequency number 1, this is frequency number 2, this is frequency number 3. If we add up these three frequencies and apply at the same time on the circuit, this waveform is going to be generated in the time domain, but it is very difficult to understand. So, what we do, we take the FFT, where this is going to split this signal into its frequency component 1, 2, 3, and now we see in the frequency domain, now the x-axis is frequency axis, and if we see the three frequency, this is the frequency 1. In frequency domain, it is just a single frequency. For example, this is 1 kilohertz, this is 2 kilohertz, this is 5 kilohertz. So, in frequency domain, this is only a single point which is at 1 kilohertz, this is 2 kilohertz, and this may be, let us say, 5 kilohertz. So, these frequencies are only a single point in the frequency domain, and the magnitude of this signal is the amplitude of this signal here. So, this is what the frequency domain signal look like, which is in time domain look very complicated, but here in frequency domain we know that there are only these three frequencies are being applied at the circuit. We can calculate the output at these particular three frequencies only. So, it helps us in solving the circuit. So, this is how we see that we have a sinusoidal signal and we can convert it into a frequency domain signal, where all these components or these frequencies which are making up this signal, they will be splitted and they will be plotted on a single x-axis as a point, and this lower limit which is we see the so many small magnitude. This is like a background noise or white noise, you can call it. These are very small magnitude of frequencies which are available, or which are kind of mathematically, if we do, there is a kind of noise or the truncation error. There are many sources to this, but now we have these three components, which shows that there are three frequency components are applied to the circuit. So, this is called the frequency domain simulations, and these are very useful to understand the circuit behavior at time domain as well, because certain characteristic of the circuit are not easy to understand in time domain. So, we bring that into the frequency domain. So, this is all for today. Thank you.